Yo, this is the physics first quarter test review. We're going to be going over chapters 1 and chapter 2. The first quarter test is a review of, it covers chapters 1 through 4, and it doesn't have any true-false multiple choice type problems. It's pretty much a math test for the most part. All right, in chapter 1, if you'll have this sheet out, this is our problem sheet. We're going to talk about the position versus time graph. And in that graph, the slope is equal to the velocity. And we're going to rework number 6 and 7 from page 563 of your book. All right, so if you'll find your book, we want to look at this graph. Right? Number 6 says, how many times does the car switch directions and during which time intervals is the car moving the slowest? Okay, it changes direction every time the slope changes signs. Okay, so it changes once here at 2 seconds, again at about 7.5 seconds, and then it doesn't change again until it starts going downward at 16 seconds. All right, so changes direction each time the slope changes sign. And in this particular case, as I showed you, that happens 3 times. All right, so the second part of the question, you got to get the book out, is during what time intervals is the car moving the slowest? Well, it's moving the slowest where the slope is the least steep. Okay, so in this case, it's moving the slowest where it has a very flat slope. All right, so that would be at 2 seconds, at 7.5 seconds, and then from about 13 seconds to 16 seconds, it's just sitting still. All right, so just make a note, fastest where slope is steepest, slowest where slope is flat. All right. So in this case, that was at 2 seconds. I'm again about 7.5 seconds. And then between 13 and 16 seconds. All right, so that's the number 6. Number 7 says, what is the instantaneous velocity at 5 seconds? That means what we're going to have to do is get the slope of the line. We need to choose a portion of the line that includes 5 seconds, and it needs to be a pretty straight part of the line. So you want to choose a portion of the line where you can easily read the graph. So I can easily read the graph at 2 seconds because the position's 2, and also at 5 seconds because the position is 0. So we need to get the slope at 5 seconds. So slope is equal to the change in y over the change in x. That's y2 minus y1 over x2 minus x1. Now, y is the position. So position 2 minus position 1 over time 2 minus time 1. Well, time 2 minus time 1, that's going to be 5 seconds minus 2 seconds, because that's where we're going to read the graph from, because we can read it. What's the position at 5 seconds? Well, it's 0. What's the position at 2 seconds? It is 2. So that's negative 2/3 meters per second. So it makes sense that it's negative because the slope is negative. So the velocity is negative at 5 seconds, and it's negative 2/3, just the slope. All right, that's the position versus time graph. The next thing we're going to look at is the velocity versus time graph on page 564. All right, so that is this graph. All right, I'm going to go ahead and do 8 through 10. So it says, over what intervals is the car speeding up? Well, it's speeding up, and I'm going to write this down in a second, but it's speeding up where velocity and acceleration have the same sign. Now, the slope is acceleration, all right? So here from 0 seconds to 2 seconds, acceleration is negative because it has a negative slope, but velocity is positive. We're in the upper part of the graph, right? 0 to 6. It's positive. So it's slowing down there, but from 2 seconds to 4 seconds, acceleration's negative, but velocity is also negative, so it's speeding up from 2 to 4. It's flat, constant velocity there. Between 7 seconds and 14 seconds, acceleration's positive because the slope is positive. Velocity's still negative, so it's slowing down between 7 and 14. Then from 14 to 16.5 seconds, acceleration is positive and velocity is positive. So it's speeding up from 14 to 16.5. But then from 16.5 to 20, acceleration is negative, but velocity is positive. So it would be slowing down. So I'm going to go ahead and write that part down. Right, number 8 is speeding up where velocity and acceleration have the same sign. And you have to remember that the slope is equal to the acceleration on a velocity versus time graph. So where do they have the same sign? Well, if you want to back up and look at my explanation again, but that occurred between 2 and 4 seconds. And it occurred again between 14 and 16.5 seconds. Everywhere else they had different signs, or it was a flat slope, so no acceleration. All right, number 9, during what time intervals is the acceleration equal to 0? Well, that is where the slope is equal to 0. Horizontal line. Okay, where's their horizontal line on this graph? Well, between 4 and 7 seconds, it's a horizontal line. And also at 16.5 seconds, we have one little point there where the slope is horizontal. Okay, so that's where acceleration is equal to 0. And then number 10, what's the acceleration at 13.5 seconds? We need the slope at 13.5 seconds. All right, so 13.5, right in here, I need to pick an interval that has 13.5 in it that is easy to read the graph. And I think it's easy to read the graph at 12 seconds and at 14 seconds. 13.5 falls in between those two, so I'm going to figure out the slope between 12 and 14 seconds. So the slope is equal to y2 minus y1 over x2 minus x1. Okay, that's velocity over time. And I said the second time was 14. First time is 12. So what is the velocity at 14 seconds? Just read the graph, and it's 0. What's the velocity at 12 seconds? Well, it's -2, so minus -2. That's going to be positive. 0 minus -2 is positive 2 over 2. Right? So that would be 1 meter per second, or meter per second squared is the way we abbreviate that, meter per second. Some books don't say the squared part. They just say meters per second. All right. So that is number 2. Now number 3 covers relative velocity. All right, number 3. Well, we need to remember that the relative velocity is equal to the velocity of what is being observed minus the velocity of what is being observed minus velocity of the observer. All right, so the problem we have is our car travels east at 27 miles an hour, our truck travels west at 51 miles an hour. Assuming east is positive, what is the velocity of the car as observed by the truck, and what is the velocity of the truck as observed by the car? All right, so the velocity of the car is equal to the velocity of what is being observed. Okay, so what is being observed is the car by the truck. Okay, the car is going 27 miles per hour east. The truck is going 51 miles per hour. So, and east is positive. So it's what is being observed, the car is 27 miles per hour, minus the truck is going -51 miles an hour, because east is positive, west is negative. So minus -51 miles per hour. So that's going to give you a positive 78 miles per hour. All right, so the truck thinks that the car is coming at it at 78 miles per hour. That's what it looks like to the truck. So that's part A. Part B, the velocity of the truck as observed by the car. All right, that's going to be the velocity of the truck, which is -51, minus the velocity of the car, which is 27. That's -78 miles per hour. So the car thinks the truck is coming at it at -78 miles an hour because the truck is traveling west. All right, so you might get a problem like that on the test, so make sure that you rework some of those from the on your owns. And let's take a look at number 4. Okay, 4, we have our 2 basic equations. So I'm not going to work a problem here. Just you got to remember that the change in velocity is equal to the change in displacement over the change in time. And the acceleration is equal to the change in velocity over the change in time. That was our 2 basic equations. And of course, the change in velocity is the final velocity minus the initial velocity. Now we changed that to just v and v naught in chapter 2, but this is the way we kind of showed it in chapter 1. All right? So don't forget those basic equations. They might come in handy. And then just know that displacement is a vector, distance is a scalar, velocity is a vector, speed is a scalar. Just know the difference between a vector and a scalar. All right, so distance doesn't have a directional component, displacement does. And also velocity versus speed. Okay, that's chapter 1. Pretty simple. Not a ton of stuff on the test from chapter 1, but you definitely are going to have to worry about those graphs. All right, let's take a look at chapter 2. So we have 3 basic equations in chapter 2. Equation 1 is velocity is equal to initial velocity. Final velocity is equal to initial velocity plus acceleration times time. Remember, we don't have an x and y component here in chapter 2 because it's always just it's kinematics, right? It's either going straight up and down or right and left. Okay, no angles to worry about. All right. Equation 2 was final velocity squared is equal to initial velocity squared plus 2 times acceleration times delta x. And then equation 3 is delta x is equal to v naught t plus 1/2 acceleration times time squared. We can't remember that the acceleration due to gravity, negative 9.8 or negative 32. If it's a free fall type of problem. Okay, let's go through some of these example problems here. This is a very good review of chapter 2. So it says, number 1 says a train slows uniformly from 15 meters a second to a stop in 3.2 seconds. A damsel in distress is tied to the tracks up ahead. How many meters away from the bound damsel must the engineer begin braking to avoid a gruesome outcome? All right, I put this problem in here because you have enough information. We kind of needed to get acceleration. Acceleration wasn't given, but we could get acceleration because acceleration is the change in velocity over the change in time. Well, the final velocity is 0 because it came to a stop. The initial velocity is 15. And the time is 3.2 seconds. So our acceleration is going to be negative 4.69 meters per second squared. So now we've got acceleration. We can get, displacement. We have time. So displacement is equal to v naught t plus 1/2 acceleration times time squared. All right, so that's going to be 15 meters per second times 3.2 seconds plus 1/2 times negative 4.69 meters per second squared times 3.2 seconds. Don't forget to square it. All right, so delta x is 24 meters. Ooh, that's not much. I think the damsel's in trouble. All right, that was a good problem because it forced you to find acceleration first, even though you weren't given acceleration. All right, number 2. An automobile with an initial velocity of 25.3 meters a second accelerates at a rate of 6 meters per second squared. Find the velocity and the displacement after 12 seconds. Okay, so we're finding 2 things. We're going to use 2 different equations. First of all, the final velocity is equal to initial velocity plus acceleration times time. So the velocity after 6 seconds starts at 25.3 meters a second. And then acceleration 6 meters per second squared. The time is 12 seconds. Okay, so that's going to be 97.3 meters per second. All right, so that automobile is cooking. All right, so that's the first part, part A. Part B says find the velocity. So we're also to find the displacement. Excuse me. So displacement is equal to v naught t plus 1/2 at squared. We could also use equation number 2. This seems to me to be the more straight ahead plug-in equation. You'd have to do a little algebra if we used equation 2. So that's going to be 25.3 meters per second times 12 seconds plus this part, 1/2 times 6 meters per second squared times 12 seconds, all squared. Okay, and together that gives you 735.6 meters. All right, so went pretty far, not almost a half a mile in 12 seconds. Okay, pause the video if you need to, and we'll do 3, 4, and 5. All right, number 3 says Tyler T. rides a scooter traveling at 7 meters per second and accelerates with a rate of 0.8 meters per second squared for a distance of 450 meters in order to clandestinely avoid an IRS agent. What is the velocity at the end of the acceleration? Okay, we know the initial velocity, we know the acceleration, and we know displacement. Okay, so if we know the initial velocity, no acceleration, no displacement, we should use equation 2. All right, our initial velocity is 7 meters per second squared plus 2 times 0.8 and 450 meters. All right, so probably going to be going pretty fast at the end of this because that's a lot of acceleration. 27.7 meters per second. So that IRS agent better have a pretty good horse to ride in order to catch Tyler T. All right, number 4 says a cood. So again, these are former students. Tyler T is a former student from my first year. Also Andrew Cood, former student from my first year. Heads a soccer ball with initial velocity of 6 meters a second straight upward. If the ball starts from 1.7 meters above the ground, how long will it be in the air before it lands? Okay, so we got a free fall problem here. Got a cood. Heads the soccer ball. That's when we had a soccer team. All right, and the ball starts 1.7 meters above the ground. So that's the height when the head hit it. And the velocity going up, it's going up at 6 meters per second. All right, so we want to know how long will it be in the air before it lands. All right, so we know the initial velocity is 6 meters per second. We know that the displacement is negative 1.7 meters. We know acceleration is negative 9.8 meters per second squared. We do not know time. Okay, so the issue with this one is we're either going to, if we use the delta x equation that has time in it, equation 3, it's going to be a quadratic formula type of situation. So we're going to have to use the quadratic formula to solve for time. So we could do that, but most students would rather just do it in two separate formulas. So we could use formula 2 to find the final velocity and then use formula 1 to find time. So final velocity squared is equal to the initial velocity, 6 meters per second, squared, plus 2 times negative 9.8 times negative 1.7 meters. So final velocity squared is 69.32 meters squared per second squared. So the final velocity is the square root of that. Okay, the square root of that is 8.33 meters per second. But there's something wrong here. What's wrong? I'll give you a second. What's wrong? You got to make it negative, because the soccer ball is going down. If you don't do that, if you forget to do that, you'll get the answer wrong. You've been better off trying the quadratic formula. Okay, so we have the final velocity. Now we can use equation 1. That's velocity is equal to initial velocity plus acceleration times time. So that's negative 8.33 meters per second is equal to 6 meters per second plus negative 9.8 meters per second squared times time. So if I move this 6 over to the left, make it negative, and then divide by negative 9.8, I'd have time is negative 14.33 meters per second divided by negative 9.8 meters per second squared. And you know you've done it right because the negatives cancel. If you get a negative time, then you messed up. All right? So, and that's what you would have done if you hadn't made this negative. Okay, you would have ended up with a negative time. Okay, so that time is 1.46 seconds. Does that answer make sense? Yeah, it makes sense. If someone's heading a soccer ball straight up, would it, and you put a stopwatch on it, does 1.46 seconds make sense? Yeah. The answers that wouldn't make sense are if you got like 0.1 seconds, right? Well, it's gonna be in the air a lot longer than that. Or if you got 40 seconds, you know it's not going to be in the air that long either. So that answer makes a lot of sense. All right, last one of our Chapter 2 review. Number 5 says, a mullet-wearing adventure seeker drops a jar of flaxseed off a bridge. If it takes 2.5 seconds to hit the ground, how high is the bridge in feet? And what is the velocity of the jar just before impact? All right, we got two questions here. How high is the bridge in feet? So I want to know delta x. All right, we know time is equal to 2.5 seconds. We know acceleration is negative 32 feet per second squared. And we know that the initial velocity is 0 because he's not throwing it down. All right, I think we got enough information if we use equation 3. So delta x is equal to v naught t. Well, since v naught is 0, that goes to 0 plus 1/2 times negative 32 times 2.5 seconds all squared. All right, that's going to give you a displacement of negative 100 feet, but we don't report heights as negative, do we? So the answer would be the bridge is 100 feet high. So part B says, what's the velocity just before impact? All right, well, we know displacement. We could use equation 1 or equation 3 here. All right, and I think the easiest one to use is equation 1. So final velocity is equal to initial velocity, which is 0, plus acceleration, negative 32 feet per second squared, times time, which is 2.5 seconds. And I think the reason that I wanted to use equation 1 instead of equation 2 is that just in case, with equation 2 I've got to take a square root. It's going to give me a positive answer, whereas if it's a negative velocity, equation 1 will give me that. And what if I got displacement wrong in part A? In this particular case, I'm just using the numbers from the problem, so I'm not going to mess that up unless I mess it up in my calculator, and that is negative 80 feet per second. So when you can use equation 1, you should use it, because equation 2 is the one you really have to be careful. All right, that does it for the Chapter 2 review. I would suggest for both Chapters 1 and Chapter 2, it says at the bottom, suggested study problems, all practice problems, and extra practice problems. So it's just how much time you have, but I'd rework all practice problems and extra practice problems from Chapters 1 and 2. As time permits, if you can only do the practice problems, that's fine. If you can only do the extra practice problems, that's fine. All right, so that'll do it for this video, and I will talk to you when we review Chapter 3.